So today we are going to see the interpretations of these two vectors v and a, the velocity vector and the acceleration vector. Suppose that s is the arc length traveled by p, where p is a particle measured from some fixed point of the path along which p is moving, and let s be increasing with time. So say this is the path along which the particle p is moving in this direction, and say this is some point which is fixed on the path from which we are measuring arc length along the path. So as the particle travels away from that point, s increases. So at some time instance the p is here, then this much is s, and that increases as time goes by. And then we consider the velocity of the particle, which by definition is this derivative dr dt, where r is the position vector of p relative to some origin and reference frame which are there in the background somewhere. Now by the chain rule, which also works in this case, I mean for derivatives of vector functions, just like it works for ordinary real valued functions, we have this. In place of dr dt, we can write dr ds times ds dt, where s is arc length. Now you already recognize this derivative. This is nothing but your unit tangent vector t hat. That means this vector at this location where p is. Tangent to what? Tangent to the curve along which p is moving. And what is that v? That v is nothing but this derivative ds dt, which is the speed of p. And the author has something to say about this thing, which is this. As in the rectilinear case, speed is just the rate of change of the total distance traveled, which in our case is ds dt, the rate of increase of the arc length. As time passes by, arc length increases, so the distance traveled here is s along this curved path. In this case it looks curved, but I mean it includes the rectilinear case as well. So what does it all mean? It means that as a vector, the velocity vector is this scalar v times t hat. So this is the direction in which the velocity vector is pointing. So next we consider the acceleration, which by definition is dv dt, the rate of change of velocity with respect to time. But just now we saw that velocity vector is v times t hat, where v is the speed. So we do this differentiation using the product rule. And that's how we get, you say we first differentiate v with respect to t, keeping t hat intact, and then in the next term we keep v intact and differentiate t hat with respect to t. Don't confuse yourself between these two t's. Okay, this is time and this is that unit tangent vector. Alright, so we keep the first term as it is. And in the second term we again apply the chain rule and write this derivative as dt hat ds times ds dt. Now ds dt is again v, so that's how you get v squared here in the second term. The first term does not change. And you already know what this thing is. When you differentiate the unit tangent vector with respect to arc length, you get this kappa times n hat, where n hat is the normal vector, unit normal vector to this curve at the point P, which is along this line, which is perpendicular to the tangent, and kappa is the curvature of the path at the point P. In place of kappa, you can also write 1 divided by rho, where rho is the radius of curvature. So what do you see here? You see that the acceleration is actually a linear combination of t of unit tangent vector and unit normal vector, and the components along these directions are respectively this. The first one is what? dv dt is the rate of change of speed with respect to time, and the second component is quite strange, v squared divided by radius of curvature. So acceleration vector points neither in this direction nor in this direction, but it's a linear combination of these two vectors. It points in some direction depending on what these coefficients are, how large or how small they are, depending on that fact. And so the acceleration vector has a tangential component dv dt, that means this component is in this direction, and a normal component speed square divided by radius of curvature perpendicular to that. The meaning of this will not be very clear right now, but it will become clear when we see these same things, velocity and acceleration, in polar coordinates. We have seen what these vectors are in a Cartesian coordinate system using x and y, those things. But in polar coordinates, we won't do that today, but in the next video, there these things will become much more clear. Now let us try to see what is going on in the special case where this curve is actually a straight line. That means if we now apply all these things to rectilinear motion, do we get something that we already know? So in the rectilinear case, this curve is this straight line. Now to keep things simple, let's keep the other conditions intact. That means, say this is our fixed point which we are considering as the origin, which we can do in this case. It's very convenient. So arc length from this origin, as measured from this origin, will be what? Will be the x coordinate of the point P, which is actually increasing with time. In fact, that was the condition. And what is the tangent to the straight line at this location P? It is the straight line itself. So what should the unit tangent vector be, which is pointing in this direction and also has magnitude 1? It is nothing but your vector I hat. So you see that if you just apply what you have found here just now, that velocity is speed times that unit tangent vector, you get back your original rectilinear velocity, dx dt times I hat. You note one more thing, rectilinear motion is not necessarily always like this, always pointing either in this direction or that direction. It can, the particle can go back and forth in some very complicated manner. So depending on the direction in which the particle is headed at some instant, the tangent vector t hat, the unit tangent vector, sometimes will be like this if the particle is trying to go in that direction at that instant. Sometimes it will be like this. Okay, so that will change. I hat, however, is always pointing in this direction. So in this specific case where we have assumed that the particle is moving rightward, so this t hat coincides with I hat. And what about acceleration? The acceleration vector in this case has only a tangential component, which of course is this dv dt, and seeing what this v itself is, this is nothing but d squared x dt squared times I hat. Why do we not have a normal component either in this direction or in this direction? That is because for a straight line, curvature is 0. Kappa is 0, so this second term is not there. Our radius of curvature is infinity. That is why. So you see that this general description of velocity and acceleration includes in it the rectilinear case as well. Now if we next think of a non-rectilinear case where the motion is not along a straight line, but at the same time it is also as simple as it can be, then we can think of circular motion, motion along a circle. And to keep things even more simple, the motion is uniform. That means the speed at which the particle is moving along a circle, that is constant. So then let's see what we get. So you consider a particle P moving in the anticlockwise direction around a circle whose center is at O and radius is B, which is some positive real number. And the particle is moving at a constant speed u. So it's moving like this. I know that it does not really look like a circle, but I try to draw it the best I can. So the particle starts its journey at this point, that is also given. At time t equal to 0, P is at B, B comma 0. Because the radius is B, so this distance is B and this is the circle. whose center coincides with the origin of our coordinate system, which we have chosen to have some x-axis and y-axis which intersect at that point O, which is the center of the circle. Now the question is this, then what are the velocity and acceleration of the particle? Since our particle P moves with constant speed u, so the arc length Bp, that means this is the point B, so this arc length Bp is also the distance the particle traveled in time t, and that will be equal to speed times time, ut. But because this arc length Bp is ut, so this angle theta subtended at the center will then be ut divided by b. Why? This is the angle in radian measure, and by definition the radian measure of this angle is this arc length divided by the radius of that circle. That's why, and the radius is b. So now we know this theta. Now using this theta, can we write down what this position vector of P is with respect to O? Yes, of course we can do that. That is because we now know how to write the coordinates of the point P in terms of this B and theta, which means the two coordinates are B cos theta and B sin theta. This is the x coordinate and this is the y coordinate of the point P. So that is why the position vector r of P with respect to O is this, B cos theta I hat plus B sin theta j hat. But now you write what theta is ut divided by B, and that's how you get the position vector in terms of what is given to you, that is B, the radius of the circular path along which the particle is moving, and the speed u, which is constant. So you now have r as a function of t. Note that here only t changes, u and b are already given, they do not change. So to find the velocity of t, you differentiate r with respect to time. That means you are having to differentiate this with respect to time. And here of course I hat and j hat do not change. I hat keeps pointing in this direction and j hat in this direction. As the particle moves, these two things do not change. So you just have to differentiate the coefficient functions. So if you differentiate the first term, which has cosine, this coefficient of t comes out. So you have u divided by b. After cancelling those two b's, you have u. But because you are differentiating cos, a minus sign also you will get. So minus u sine of ut divided by b times I hat. Similarly, if you differentiate this, you are going to get b times u divided by b, which is u, times cosine of ut divided by b j hat. So this is your velocity vector. Now from this velocity vector you can calculate its magnitude, which if you actually do, what will it be? It will be square root of this coefficient square plus this coefficient square, which becomes square root of u square. So that will be equal to the absolute value of u, but because u is positive, so you just get u. So you see that this thing is constant, it's not changing, it's fixed and it's u. Now next we similarly have acceleration, this time by differentiating velocity with respect to time. And you can go through the calculation yourself. This is what you get, minus of u square divided by b cosine of ut divided by b I hat, minus u square divided by b sine of ut divided by b j hat. And if you go back, you don't have it here, but if you go back and see what our vector r is, then this thing becomes minus of u square divided by b square times r vector. So this is positive, and because you have a minus sign, why is this positive? Because it's a square and you have a minus sign, so that means it's negative. A negative scalar times r is your acceleration. So r is pointing in this direction, so acceleration will be pointing inward towards the center. That we have come to see from this calculation. But what about the discussion we had just now? What is that discussion telling us about acceleration? Let's see that also. Now by that discussion, acceleration is du dt times t hat plus u square divided by rho times n hat. I did not write v here because it's given that speed is u, so straight away I wrote u. T hat and n hat, you already know what these things are, unit tangent and unit normal vector, and rho is the radius of curvature. Now u is constant, it does not change with time, so the first term vanishes. There is no tangential component of acceleration. This term, however, stays and it becomes u square divided by v. For a circle, at every point, the radius of curvature and curvature, they are the same. Well, I don't mean they are equal, but radius of curvature, that quantity does not change as you move from point to point on the circle. Similarly, curvature also does not change, and radius of curvature is nothing but the radius of the circle. So you write b in place of rho. So what are you getting? Here you are getting that this is the acceleration vector, but you have already seen that the acceleration vector is pointing in this direction. So this also tells you that the normal vector is pointing in this direction. It's opposite to the direction in which the position vector is pointing. So it's matching. Let's see an example next. A body is being whirled around on the end of a rope at the constant speed of 10 meter per second. If the body moves around a circle of radius 2 meter, we have to find the magnitude and direction of its acceleration. Direction you already know, towards the center, but what's the magnitude? So in the solution I don't write much, I just simply write what the magnitude is, and that is from what we saw just now, 10 square divided by 2, constant speed square divided by the radius of the circular path, which is 50 meter per second square. This is slightly less than 5 times the acceleration due to gravity on Earth's surface. And let's end the video here. In the next mechanics video, we are going to see velocity and acceleration in polar coordinates.